Now we want to show that the derivative of x to the power n is equal to n times x to the power n minus 1 if n is a positive integer. So how can we show that here? So here we have given the function as f of x is equal to, let's say, x to the power n. So we have this power function where n is actually a positive integer, right? So that's what we have given over here. So we need to understand that fact, okay? So we have f of x equal to x to the power n. And our goal is to show that if f of x equal to x to the power n, then the derivative is given by this formula over here. So let's try to see if we can show that. Okay, and we're gonna do this by using the what is that rule called, what was the definition of the derivative? That's what we're gonna use it. Okay, and so what is the definition of the derivative? If f of x equal to, if you have f of x as a function, then f prime of x is equal to, find the difference quotient of the given function, which is f of x plus h minus f of x, right? And everything underneath that will be h. So that is the difference quotient, and then we just want to see where that difference quotient approaches when h approaches to 0. So that's what we want to do it. Okay, so let's try to compute this. All right, so what is the task here then? We first need to compute the difference quotient, and then so let's try to have that. So we need to have a function which is given over here as x to the power n. So write that down as x to the power n. We need to evaluate the function as x plus h. So if this is the function, replace x by x plus h, and then we get that as x plus h to the power n, right? And then we have a difference between these two, so have that, and everything underneath that will be h. So that is our difference quotient, right? So whatever difference quotient we need it, and then we just need to find the limit of these as h approaches to 0. So and then that will give you the derivative. So this is what we needed to do it. But now, since we have already the difference quotient, but if you try to find the limit at 0, you can see that the bottom approaches to 0, the top function also approaches to 0. In that case, we will have the indeterminate form. So if you have the indeterminate form, then how do you compute the limit? One of the idea is to, if you have the indeterminate form of the 0 over 0 type, then we just want to see why that is 0 at the bottom, why that is 0 at the top. That means see if there is a 0 common factor at the top and bottom, and we just try to cancel that out and then find the alternative expression. Okay, so let's try to do that then first. Okay, so what can we do here? How? So you can see here the denominator is 0 because of h. Can we find that at the top as a common factor? Directly, I don't see that, right? But let's try to see if I can expand this expression. And expanding the top is not straightforward, but I'm going to see if we can expand. What I want to use here is, okay, I know how x to the power n works, right? I mean, that is just x to the power n. But what does the x plus h to the power n mean? That means if you multiply x plus h n times, what do you get? Now everything over here look like kind of abstract, right? But what we can use here is one of the beautiful theorem. It's called binomial theorem, which will help you to actually expand this type of expression. So the binomial theorem says that if you have x plus h raised to the power n, is something like that, then x plus h to the power n will be equal to x to the power n plus n times x to the power n minus 1 times h plus n times n minus 1 over 2 times x to the power n minus 2 h square plus n. Okay, so and then we continue the term like that, and then dot dot dot, let's say, and then plus n times x to the power h n to the power n minus 1 plus h to the power n. So this is how we can expand if you have x plus h to the power n kind of term. Okay, so if that is the case, why don't we use this expansion over here on the top of this difference quotient, and then try to see if we can simplify this. Okay, so let's try to do that. So what we get here after this is f prime of x is equal to, we need to evaluate the limit as h gets closer and closer to 0 on this expression. which is what is the expansion of x plus h to the power n, whatever we have just written. So let's say copy that again. So n times x to the power n minus 1 times h plus n times n minus 1 over 2 x to the power n minus 2 h square plus dot 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 plus n times x to the power x times h to the power n minus 1 plus h to the power n. So this is the expansion of x plus h to the power n, and what we have on the difference quotient is x to the power n, right? So if that is the case, write that down. So distribute by the negative sign. On this case, very easy to do that, right? And everything underneath that will be h. What is the benefit of expanding these? We have these two terms we can combine, and then we get 0. And I didn't see any other benefit. Directly still each term is vanishing to 0 at the top and then the bottom. But now I can see one thing over here is I can actually take h out as a common factor, right? So if I take h out as a common factor at the top, then I get n times x to the power n minus 1 is the remainder on the first term. In the same way, on the second term, I'll have n times n minus over 2 times x to the power n minus 2, and 1h is taken out. So we'll just have 1h left over. In the same way, each of the invisible term over here is involved with here, so we can take that out. And then over here we'll have n times x times h to the power n minus 1 is there, right? But if we take h out over there, the remaining factor would be h to the power n minus 2, plus when we take h out from h to the power n, we get the remaining factor would be h to the power n minus 1, and everything underneath that will be now h. And do you see a 0 common factor? Well, yes, right? So we can just cancel that out. But when we do that, you can clearly see that when h gets closer and closer to 0, the first term is independent of h, so it will be always like that. But the second term, you can see there is yes, so everything approaches to 0. All of these invisible term involved with yes, they approach to 0. This term approaches to 0. That term also approaches to 0. So if that is the case, you can clearly see that the difference quotient of this function x to the power n, when you take the limit as h approaches to 0, we just get n times x to the power n minus 1. Right? So that's how we get, because this is the only term left over. So if that is the case, this is the derivative of x to the power n, and which is actually known as the power rule. Okay, and this is actually, you can also consider as a proof of the power rule when n is the positive integer.